Thanks, Brittany, and morning, everyone. As Brittany said, I'm going to talk a little bit about the work that we're doing to evaluate and understand climate impacts on U.S. Pacific coral reef ecosystems. First, I want to acknowledge the very many CIMAR staff who have been involved in this effort over the past 2 decades, and also emphasize just how absolutely mission critical CIMAR is to our long-term research and monitoring mission in the Pacific. I want to start by giving a very general overview of the types of climate-related coral reef data that PIFSC collects and highlight some of the major results and ways in which our data are being used. Within the archipelagic areas of the US Pacific region, PIFSC long-term ecosystem monitoring is conducted as part of NOAA's National Coral Reef Monitoring Program, or NCREMP. Starting in 2013, NCREMP has collected co-located climate and biological data, typically on a rotating 3-year cycle. NCREMP tracks ocean temperature and seawater chemistry, allowing us to track ocean warming and ocean acidification, as well as benthic and fish communities and ecosystem processes like reef accretion and erosion that we expect will be particularly sensitive to climate change. This rich, multidisciplinary data set in an otherwise fairly data-poor region provides us a long-term perspective on the status and trends of coral reef ecosystems. Touching briefly on each of our climate-related data streams that we collect as part of NCREMP, we maintain a vast network of temperature loggers across the Pacific Islands that we deploy at several depths around each of the islands and atolls where we work. You can see all the locations as the yellow dots in this picture here. These loggers provide in situ subsurface temperature that tells us what temperature regimes and thermal stress look like at the benthos where the corals themselves live. These in situ time series data can also be used to ground truth satellite ocean surface data and subsurface hydrodynamic and climate model output. For example, a recent analysis led by Jesse Perlman demonstrated that ROMS models, developed and discussed previously by Brian and his team, shown in this figure in blue, accurately captured subsurface temperatures as collected by our NCREMP temperature loggers, shown in black, in the main Hawaiian Islands between 2011 and 2017. This gives us confidence in the accuracy and representativeness of these model outputs. And over the next few years, NCREMP data will continue to be used for the validation and calibration of efforts like CEPHI that Ryan talked about earlier, and other climate modeling efforts in the region. Our past decade of NCREMP climate monitoring has also highlighted the strong natural gradient that exists in carbonate chemistry, in pH, and aragonite saturation state across the broader Pacific region. This map shows our in situ average aragonite saturation state for each of our islands and atolls, with interpolated GLODAP aragonite saturation state in the background. What we find from our data is that aragonite saturation states vary pretty dramatically, from a low of about 2.9 in the northwestern Hawaiian Islands to values in the low 4s in American Samoa in the South Pacific, more or less the range and the delta that we expect will occur on most reefs over the next few decades. This large gradient in carbonate chemistry allows us a glimpse over space of what the trajectory of coral reefs may look like under ocean acidification through time over the next few decades. Based on laboratory experiments, we expect that processes like coral calcification and reef accretion will be sensitive to ocean acidification. And consistent with this, when we examine data from our calcification accretion units, or CAUs, across our Pacific Islands, we observe an exponential decrease in reef accretion rates with decreasing saturation state. This is mostly due to the calcification of crustose coral and algae. This suggests that accretion and, by extension, reef habitat production may be among the ecosystem processes most sensitive to ocean acidification. It's therefore critical that we continue to track and understand processes like reef habitat production if we want to understand climate change impacts on coral reefs. Given this observation from our long-term NCREMP monitoring, we've recently begun to invest additional effort and to better understand carbonate accretion and reef habitat production and persistence. And we've been doing this using carbonate budget assessments. I find it most intuitive to visualize a carbonate budget as a balance or scale, where on the one side of our scale we have our carbonate production. That's from calcification of corals, crustose coral and algae, and other marine calcifiers. And on our other side of the balance, we have our carbonate erosion from urchins, from parrotfish, and from other macro and micro bioeroders. When we conduct a carbonate budget assessment, we're determining where that balance shifts, what the relative rates in production and erosion look like. This is important because in order for a coral reef to persist, especially after a disturbance or while under stress, the rate at which a reef is growing must outpace the rate at which it's being eroded away. We can use carbonate budget assessments and their results to place our reefs into 3 different categories or carbonate budget states. Our first on the left is our net production state. This is our state in which production is greater than erosion, reef habitat is being produced, and a reef is likely to persist through time. Our second state, all the way on the right, is our net erosion state, where erosion rates are greater than production, reef habitat is being removed, and a reef is unlikely to persist into the future. In the middle, we have our equilibrium state, where production and erosion are more or less equal or balanced and reef habitat is being maintained, depending on a multitude of factors may persist into the future. We're using a census-based approach for calculating carbonate budgets that's based on Chris Perry's reef budget methodology. This requires collecting information on, for our carbonate production side of the equation, the size and abundance of corals, of calcifying algae, other organisms on a reef that produce calcium carbonate material. And on the other side of our balance, size frequency data on urchins and parrotfish and other bioeroders. We then integrate these census data with a taxon-specific database of calcification and erosion rates to ultimately calculate our site-level net carbonate production estimates. If you'd like to learn more about the databases that we've built for the Pacific Islands region, I'd encourage you to visit Candace's poster if you haven't already. Several years ago, we realized that we wanted to add carbonate budget assessments to NCREMP. However, we immediately encountered a logistical conundrum. Historically, these data have all been collected in water by divers, but the time required for these complex surveys was significantly greater than what our task-loaded and time-limited program could support. So we needed a way to increase the efficiency of our data collection while still maintaining the accuracy and comparability of the data that we collect. Thus, we sought instead to conduct our assessments using structure for motion, or SFM, imagery that we already collect as part of our NCREMP monitoring. Our extraordinarily talented CIMAR team has been developing tools over the past couple years that allows us to replicate in-water data collection in a structure for motion environment. For benthic data, we use orthomosaics and digital elevation models to identify and size benthic substrate components along 3-dimensional rugosity transects. You can see an example of this on the bottom. And then using object detection techniques to identify and size urchins within a belt transect survey area. My mouse doesn't work, but you can kind of see a picture of an urchin in that second image from the bottom. Unfortunately, SFM-based methods don't currently exist for fish surveys, so we're still conducting those using diver-based data collection techniques. We're really excited about the potential of this tool, but before we could roll it out in real time, we first needed to compare our data with in-water data to determine whether we were introducing any kind of methodological bias by shifting from in-water to SFM-based data collection. Between 2021 and 2023, we conducted a series of in-water versus SFM methods comparisons at sites around Oahu, in the Mariana Archipelago at Guam, Saipan, Pagan, and Maug, and in American Samoa at Tutuila and Rose. These sites represent a range of different reef habitat types, community compositions, and working conditions. There are quite a few data sets and analytical and processing steps that go into calculating a carbonate budget. So for the sake of simplicity here, I'm cutting to the chase and just showing our overall net production results. What we're looking at here are net carbonate production results that's calculated as production minus erosion for each of our 18 pilot survey sites. On the left, each of the bars is for each of our sites, the colored by island and then shaded light versus dark by method. On the right, we're looking at the same data where a point is shown for each site, the in-water versus SFM carbonate production. The black line is the line of best fit for the data, shown with a gray dashed 1-to-1. Overall, we found that there was no significant or systematic methodological bias between our in-water and SFM-based methods. What this means is that we were successfully able to reproduce in-water surveys traditionally conducted by divers using structure from motion. We did observe a few site-level differences at a couple of these sites, particularly in areas that were structurally complex or highly biodiverse. We expect this has to do with differences in measurement resolution and/or difficulties resolving cryptic species. However, we deemed this pilot a success, and as of this year, we've now added carbonate budgets to our long-term NCRIMP monitoring. We collected our first set of data across the Hawaiian archipelago this past summer. Slightly shifting how we're viewing our data now to get back to the original question of which of our carbonate budget states each of our reefs falls into. Of our 18 study sites, the 16 shown shaded in blue fall into our net production category, where reef habitat is being produced and is likely to persist. 2 of our sites fell into our equilibrium state, where production and erosion were more or less balanced. Fortunately, none of these 18 sites fell into a net erosional state, which I'd offer is a good sign for the condition, at least of these sites. Looking forward, over the next several years, we plan to extend the spatial and temporal scale of our assessments across the Pacific Islands, particularly targeting that strong natural gradient in pH and saturation state across the Pacific Islands. We're also working with several collaborators, including Brian and his team, the NCRIMP team in Florida at AOML, and the University of Exeter, Chris Perry and his team, to use our data to evaluate future projections in reef habitat persistence under different climate, management, and adaptation scenarios. Ultimately, we intend to provide decision support tools to coral reef managers who are looking to best, most effectively, and most efficiently manage coral reefs under a rapidly changing climate. If you'd like to learn more about any of the results or methods that I've presented, or would like to work with our data, we love sharing all of our NCRIMP data, please feel free to contact me at this email address. And if we have time, I'd love to take any questions. Okay.